problem number 1. Imagine a situation like this, where you have, let's say this is the horizontal, and on this horizontal is resting this uniform rod. Okay. And the weight of the rod is 124 newtons. Now, at the extreme right end of the rod, you have applied force F, which is equal to, forgot the number, it's 100 newtons. Yeah. It's 100 newtons here. And the rod makes an angle of 30 degrees with respect to the horizontal. And the angle that this force makes with respect to the direction of the rod is, this is 40 degrees actually, and this is 30 degrees. Okay? Now, you have applied another force here, F, such that the rod maintains its static position, it's at rest. So you have to find out the magnitude and the direction of this force vector. Is the situation clear? We have a rod here, a uniform rod. What's the sense of the term uniform here? It's such that the center of mass of the rod is exactly at the center. Whatever the length of the rod is. The length of the rod is not relevant here. We do not need it. So, three forces are essentially acting on it. One is the weight force, which is exactly pointing downwards from the center of mass of the rod. The second one is this force of 100 newtons making an angle of 30 degrees with respect to the direction of the rod. And the unknown force F, which makes a certain angle with respect to the vertical or horizontal. And we have to find out what this force F is. So the question is, here, the question is to figure out the vector F. And since it's a vector, you need the magnitude as well as some sense of direction, which the angle will give. Okay. So it's a static problem. There is no motion or dynamics involved here. What do you do to solve this problem? What is to be done? Exactly. Break up the forces into components along the horizontal and the vertical and just balance the forces. This is just applying the second law of Newton, which is the sum total of all the forces will have to be equal to mass times acceleration. Now obviously in this problem everything is static, so the right hand side is 0. That means the sum of F will have to be equal to 0. Right? When you do this, that means component-wise, along the x and along the y, in both these directions, the sum total has to be 0. So what we will do here is break up each of the forces into corresponding x and y components. That's your standard xy. You just follow this and break up every component along the x and y. So the W, the weight force, is already pointing along the negative y. No need to split that up. Right? What about this force of 100 newtons? See,
F cos 30.
You can do a quick geometry here and figure out that this angle here would be how much? 70.
60 degrees.
The entire angle would be 70, but only this one would be 40, right? Because these and these are alternate angles. Okay. So that means this component here along the horizontal would be 100 cosine 70 degrees.
It into alternate
Along the
angles.
plus. The
It
vertical
into
one
alternate angles.
would be 100 sine 70 degrees. the vertical and the horizontal components, this we have talked about while discussing the Cartesian system of vectors and all that. So look that up. It may not always be the case that the vertical component gets a sign. It all depends upon which angle you are considering. Because this angle is 70 degrees, then the component adjacent to this vector, 100 newtons, gets a cosine. But suppose this angle had been under consideration, then this would have picked up a cosine. So it's not a hardcore rule that the vertical is always a sine and the horizontal is always a cosine. Depends on the angle that you have taken. Okay, and then finally this force has to be split up into vertical and horizontal components. Let's say this angle here is alpha. We do not know what angle this is. Well, this by the way does not make a 90 degrees with respect to the rod. This might be from the figure it might seem the way I have drawn it makes an angle of 90 degrees long. It's some angle, let's call that angle alpha with respect to the vertical. So this would be a cosine, the vertical one, and this would be an f sine alpha. Okay, so we have split up each and every force under consideration into the corresponding x and y components. All we need to do now is sum up all the components along the x and equate that to 0. So let's do that first. So what are the forces, what are the components along the plus x?
100 cos
100 cosine 70. Right? And minus f sine alpha. Why it's a minus? Because it's pointing along the minus x. That's important. And that equals 0. What about the sum of fy equal to 0? 100 sine 70
f cos
plus f cosine alpha, right?
minus 124.
Minus the wave force, which is 124, and that equals 0. So you see two equations and two unknowns, the unknowns being f and alpha. You should be able to figure it out. And the way to do that is you isolate f sine alpha, which is equal to 100 cosine 70, and from this equation it's f cosine alpha equals 124 minus 100 sine 70.
divide.
Then what's the easiest thing to do in order to find out the magnitude? Square it. Square it. So square each and add those up. Sine squared alpha plus cosine squared alpha gives you 1. So f would be the square root of whatever this squared comes out to be plus whatever this squared comes out to be. If you have a calculator, then you can, not now, but whenever you, in the exams and all, put in cosine 70, sine 70 and do the calculation. So, I think it comes out to be some 45 units or something. And this is not yet done because this is just the magnitude. Remember, this is a vector we are talking about. So, the angle has to be figured out. So, divide this by this, f gets eliminated out, and you have tan of alpha equals 100 cosine 70 divided by 124 minus 100 sine 70. Once you have the right hand side numerically, take the tan inverse of that to get the angle. Pretty simple exercise in statics. Alright, any questions? Okay, so let's move on to another one, and this would be on something called the Atwood's machine. This is problem number 2 now. I would suggest that although at some point, if not immediately, I would like to upload these over VTalk. I mean, the problem that we discussed or the discussions in class. Slides are easy to upload, but these handwritten notes I need to scan them. The alternative is I'll have to really typeset those equations, which is more time consuming. I do not really want to do that. So I would rather prefer to have handwritten notes on my own folder, paper, and then scan those and upload those over VTalk. But it seems that VTalk is having some problems both for you and also for me. Also for me in the sense I don't find my updated list. Although I could upload material over VTalk, I cannot really access your attendance list. So I would strongly suggest that you keep on taking notes in class. That's the way you learn as well. Learn better, I think. Whatever you're seeing here on board being worked out, take notes and work those out yourself in real time if possible. The semesters are really short. You have just started and almost two weeks are done, and within a couple of weeks you'll be having the CAT. Not exactly within a couple of weeks. I don't want to scare you, but yes, you understand, right? So 3 CATs in 3.5 months. And also you'll be having assignments and quizzes. At least we should have 1 assignment and 1 quiz before CAT 1. So hopefully next week sometime, maybe next Friday, I'll let you know next time. We will probably have a class quiz next week. Okay, so the second problem that I wanted to talk about is something called the Atwood's machine. Does anyone know what an Atwood's machine is? These are the simple mass pulley systems. Machine is something which makes your life easy. As whom said?
Amir.
Right. You got that. In
3 days.
Okay. And what's the actual definition of a machine? You remember that? Okay. So the mass pulley system. Let's say we have 2 masses, M1 and M2, right? And they're connected via a single rope or single string, one piece of string. So this simple setup is something called the Atwood's machine. And the pulley is considered to be frictionless and massless. Now we have to find out the acceleration and the tension in the system. The acceleration of the system and the tension in the system. Now, let's say M2 is greater than M1. That means this mass being heavier, this would tend to accelerate downwards, and this guy will move up with the same acceleration. Why is it the same acceleration? Because it's the same system, connected to the same. Now, what's the common approach here? The first thing that you need to do? MG. Yes, but before that, the standard roadmap of all these force kind of problems is to draw free body. Exactly. The first step is to draw something called free body diagram. What do you mean by that? It's like all the forces, if you consider one particular mass involved in the problem, let's say there are 2 masses here, M1 and M2. We need to identify and draw along with the directions all the possible forces acting on that particular object. That's the first step. In any kind of, this is the simplest application possible. But obviously there are more complicated versions where you have these inclined planes and friction and all involved, right? So there, it's very essential from the very beginning to have the right free body diagram. Unless you have the correct force diagram, all the follow-up calculations would be messed up and wrong. So, first step is to draw the free body diagram. That is essentially to say, identify all the forces along with their directions acting on any particular object or each particular object involved in the problem. In this case, namely M1 and M2. So let's do that the diagram itself. So for M2, you have the weight force acting downwards, M2G, and then the tension due to the string pulling it up. That's all. Then from M1G, similarly M1G pointing downwards and the tension pulling it upwards. Again, it's the same tension because it's the same string. Different parts of the same string or rope cannot really have different tensions. Otherwise, the string would have been torn apart. So both are T. Okay. Next, what you do is, the next step is, once you have drawn the free body diagram, next step is obviously to apply Newton's second law, along each of the directions involved. In this case, it's only the vertical, so it's just one dimension. So essentially, in this problem, we will be summing up Fy, this being the y direction, the vertical one, and that would be equal to m times a suffix y. So let's do it for M2 first. So for M2, so we need to do it for each of the objects, each of the masses. So for M2, what do we have? You need to take care of the correct directions as well, because these are vectors and the sign conventions need to be followed. So anything which is pointing along the plus y would be assigned a positive sign, and anything pointing downwards picks up a negative sign. So T, the tension, minus the weight force, M2G, will be equal to minus M2A. Why is it a minus for M2A? Because it's pointing downwards. M2 being heavier than M1. Okay. And for M1, it would be again be T minus M1G, and that will be equal to, now it's a plus. So it's M1. Okay. Any questions till now? Good. So again, in order to find out A and D, which are the question marks here, all you need to do is solve this simultaneous set of equations for A and D. Two equations, two unknowns. Exactly solve them. You do that and you should get the answer as A equals M2 minus M1 divided by M1 plus M2 times. That's it for the acceleration. Now, you should always do quick checks as to whether the final answer is making sense. See, it's an acceleration, right? So it should have units of g. G is the acceleration due to gravity. If you have had a factor of mass contributing in front, that would have been wrong. But you see, this is only a ratio of masses, and essentially the unit of mass will drop out. It's mass divided by mass. So you are doing good. Had it been that you had obtained the answer by doing the algebra as M1 times M2 times G, for example, that would have been wrong, because dimensionally they do not make sense. So these are quick checks that you should do. Also, let's say wrongfully you had assigned a direction of A, since we know that M1 and M2, M1 is less than M2. But suppose you had taken this A for M2 to be upwards and this to be downwards. Then this would have flipped sign. So the answer would have come out to be negative, which would have automatically told you that the acceleration that you have chosen is actually just the opposite. The actual acceleration is just the opposite. But since we have already chosen the correct direction, and M2 being bigger than M1, this will come out to be positive. So the direction is okay. Okay. So these are like quick checks for you to make sure that the physics that's coming out of the problem is actually okay. Okay, and just put in the value of A here in terms of M1, M2, and
So
G.
why don't we simply divide?
Huh?
Why don't we simply divide?
Divide it, yeah, that's also easier, right? That's also easier. What he's saying is you can divide each of these equations and get rid of A in order to find out the tension. So then the resultant equation will just involve D. Then you just solve for it. That's also. All these are equivalent. Or since you have already obtained these, you can use any one of these, substitute into here and get the value. Okay. 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 So let's do. Is that okay? Any questions here? Okay. So let's do another one, which will again an example of Atom's machine, but rather on a table plot involving two masses. So it's a situation like this, where you have two masses, one resting on the table and connected to another mass which is hanging free. Okay, so let's say this is M1 again and this is M2, and again as before you have to find out the acceleration and the tension. So as before, what we do is we draw the free body diagram. To do it for each, so for M2 it would be M2G as before, and the tension in the string, the same tension as the tension through via which the M1 is being pulled, and furthermore, because it's resting on the tabletop surface, apart from this M1G, which is always there, you have
Normal
a normal reaction due to the table onto the block M1. So the first situation we'll consider is without friction. Even if you do not have friction, I mean, it's always strongly recommended that you write down or draw all the possible forces. N may not be directly relevant here in this calculation because friction is absent. But once friction comes in, as we'll do next, then you have this mu n factor. But nevertheless, while drawing the free body diagram, identify all possible forces and draw them to complete the friction. Okay. And remember, tension is always a pulling force. So, with respect to each of the masses, you have the tension pointing away from the body. So, this one is actually pulling, this one is actually pulling. But if you think of the third law, and if you're wondering as to what happens to the reaction pair, the reaction pair will actually act on the string. So, if you draw the free body diagram of the string, then the tension directions will actually be reversed. So that's how action-reaction pairs work. If at all you are wondering about what happens to the reaction force will appear in the free body diagram for the string, which you are not interested in. You are interested in the masses, the movement of the masses. Okay, so this guy accelerates downwards, and with the same acceleration,
towards right.
the mass M1 will move towards the right. Again, assign coordinates x and y. Right? And we do the same exercise. Sum of f equals f times m. Just the application of the second law of gravity. Okay. So, what do we have here? Let's do it for M2. Let me erase this. So it's M2G. Sorry, P minus M2G equals minus M2A. Same as before, right? And for this one, we'll follow the horizontal towards the right will be the positive direction. That's like the plus x-axis. So for M1, it's just T equals M1A. So initially, we have the assumption is that the system was at rest initially. You have started the system from rest and then released it. After it has been released, this is the dynamics. Okay, so as before, you solve for T and A and get whatever the answer is. Needless to do that again. Okay, so this was an example without, this is without friction. Now how does things change with friction?
Additional force opposite to tangent.
What's the additional force that you need to take into account? You have friction. It's obviously the friction force. Because the movement is towards the right, you have a friction force which is
left.
opposing it towards
Left.
left. And the magnitude would be given by, the coefficient of friction is mu. It's mu times n, which is mu times m1 times g. Why is it mu times why is it mu times m1 times g? Because
Normally action.
from vertical equilibrium for the mass m1, you have n equals m1g. Had there been a vertical acceleration as well, for some reason, not for this example, then for the vertical direction as well, it would have had an acceleration. Okay? But this is assumed that it always stays on the horizontal. It doesn't leave the surface. So automatically n should balance m1. So that's how it is. So this equation, the first one with friction, doesn't get changed. It's still the same. This part, the hanging one. The force equation for this one will change. Now you have T
Minus mu.
minus mu n, which is mu m1g, to be equal to m1 times. So do this calculation and again find out A and T. And what, again a quick check is, so you have your calculation for A and T without friction first. That was the first case. Now you have it with friction involving this mu. If you substitute mu equal to 0, you should recover the result for part 1. So these are how you should actually cross-check your results and convince yourself that you are actually doing things right. Without friction, take away friction, you get back part 1. Okay? Any questions till now? Again, stuff which is kind of known, but again, since we're going through Newton's laws and its applications, this is the very first step. Okay, now let's take up another one where rather than having horizontal surfaces, we'll have inclined surfaces. I'll erase this. Okay, so now let's consider this problem here. So let's say this is problem number 3. You have an inclined plane on which is resting this this mass m. M. And this incline is making an angle alpha with respect to the horizontal. And in the first situation, let's consider again the case, like in problem 2, the case without friction. So there is no friction between the surface of the block and it. What you are doing externally is applying a force horizontally in order to maintain the block at rest. again it's a static problem. There is no motion involved here. What you have done is, you have applied, let's say, an external force L to keep the block at rest. Obviously, because it's an incline without friction, not apply an external force, it will fall down. So you have to find out this force L. So the question is, what is this F vector? Is the question clear? You want to repeat me? You want to repeat the question? Okay. So again, what should be the approach? Components. And now you have two choices of choosing your axes. One is the standard vertical ones, like we have been doing X and Y. The other choice, maybe a more convenient one, would be a slanted one, right? Where the x-axis is along the incline and the y-axis is perpendicular to the incline. Okay. But before that, let's choose one set. Let's choose, because we have been doing this. This is already pretty straightforward. Let's do the slanted one. You should understand also that the choice of the coordinate axis do not make a difference to the actual result. The choice of coordinate system is to make the calculation more convenient. Whatever coordinate system you choose, take a simple example. You want to find the position of an object. Let's say again our popular example of the rocket launch. You want to find out the position of the rocket after you have launched, after 10 seconds. Suppose you choose a Cartesian system attached to the Earth, or a cylindrical system of coordinates, like we discussed before, or a spherical one. Do you think the position of the rocket will change depending upon the coordinate system? No, it won't, right? It's up to our convenience as to which coordinate system eases our calculation. Depends upon the symmetry of the situation and so on. So likewise, if you choose just the vertical ones or the ones which are inclined like this, all you've done is you've just rotated the coordinate system. So now my x-axis would be along the incline and my y-axis would be
perpendicular
to the incline. Okay, so now let's draw the free body diagram of the block. The first one obviously is